Everyone, looks like our attendees are leveling off here, so I think I'll go ahead and get started. First off, I'd like to thank everyone for joining us today. If you've attended one of our previous webinars, it's great to have you back, and if not, welcome for the first time. My name is Rich Poltar, and I'm an applications engineer here at Zygo, based out of our Middlefield, Connecticut office. Also helping out on our end, we have Scott Kottmer, who's another applications engineer based out of our offices in Santa Clara, California, and Eddie Lavilla, also an applications engineer here in Connecticut. They'll both be monitoring our chat here throughout the day, so if you have any questions, feel free to ask those at any point, and they'll do their best to either respond right away or bring those up as we're going through here for a discussion with the wider audience. Okay, so first I just wanted to give you an idea of how this GoToWebinar screen here is laid out. So it's split between pretty much two screens, your main viewing screen and then a dashboard on the right. Here in the main screen, you have the slider where you can adjust the relative size between the webcam view and the presentation view. And as we go through the presentation today, there might be times where you want to resize the webcam, just because we'll be taking a look at some live measurements on an instrument with the webcam. And then on the right, if you'd like to hide that dashboard, you can always click this orange rectangle with the white arrow inside of it. And right below that, you can also toggle in and out of full screen mode, where at times it might be helpful to have a larger view of the presentation or webcam. And then below that, there on the dashboard, that's where you can go ahead and submit any questions. So as I said, Scott and Eddie will be taking a look at those questions as they come in. Please feel free to ask those at any point, because they'll be checking that out throughout the entire webinar. Okay, so what are we going to talk about today? The first thing we're going to discuss is the effects of vibration and the impact that vibration has on traditional phase shifting interferometry, or PSI measurements. Next, we'll then go over some of Zygo's solutions for dealing with these effects. Specifically, we'll take a look at Q PSI and Dynaphase. These are two measurement types that Zygo developed to mitigate vibration. And we'll review how each of those work. And then I also will perform some example measurements here with an instrument that I have here, so you can see that process and that workflow and how effective each one of these measurements are. And finally, then, using the Dynaphase measurement mode, we'll take a look at some dynamic alignment techniques. So here's a picture of the setup I'm working with, just to give you an idea of where I'm at. Here on the left, you see I have a standard verifier interferometer, and I'm using a 4-inch, 4% reflectivity transmission flat as my reference element there. And then throughout the day, we'll be looking at two test parts, one of which is another 4-inch, 4% reflectivity TF mounted in a 2-axis motorized tip tilt mount. And then the other test part we'll look at in the dynamic alignment is a 2-element beam reducer. So this is just a 2-inch singlet and another 1/2-inch singlet lens that we're using to reduce the beam from 2 inches to 1/2 inch. And finally, you may notice the hardwood floor there. I am actually on the second floor of my house. This is an old house built in 1923. So we have a lot of squeaky floors here. And actually, as I roll around my office chair here, you might see some of the effects on my alignment and definitely on my measurements. So just want to point out, this is definitely not your typical optical metrology station. Okay, so PSI is very sensitive to vibration, and I imagine many of you have had to deal with this before. You know, it might be on your production floor or in your clean room, or even in more stable environments, but there always seems to be some source of vibration that we have to deal with when performing these high precision measurements. So the images on the right actually show how vibration typically affects some measurements. So you see on the bottom there, that is a PSI measurement, or conventional phase shifting interferometry measurement, where you can see that ripple, or what we typically refer to as fringe print through. And you see that there in the data on the lower right. And that ripple will then correspond to the fringes in the interferogram right above that. So this ripple or print through is really the telltale sign that and the best way to know we have vibration affecting our measurement. It's also important to realize that the higher quality of your part, really the more these effects are going to affect your measurement. The amplitude of the errors caused by vibration are actually going to be driven by the amplitude and frequency of that vibration in your environment, and regardless of your test part. So the higher quality tests you're trying to perform, the more and more noticeable those effects of vibration will be. And finally, I think it's always important to point out that this is not just a visual effect on your measurement. This vibration will have a real impact on your numerical results. So for lower quality parts, if you're in a pretty good environment, the vibration effects might be in the noise and you might be able to get adequate results, but in most cases, you're going to have to do something to deal with vibration. So one case where this is especially true is when you're doing any type of spatial frequency analysis. So when you have such a dominant ripple in the data, it really becomes really difficult to analyze for mid-spatial frequencies. Okay, so now let's take a look at some typical ways we normally deal with vibration. The first of which here is pretty clumsy sometimes, but it involves coupling the cavity. So I'm going to switch over to my instrument here. And what we mean by coupling the cavity is actually taking something and bridging the gap between the interferometer and the test part. So in this case, I've just kind of taken a 1x4 piece of wood here and bridged that gap. And you can maybe notice that the fringes have stabilized a little bit here on our live display. And if I pick that up again, it's tough to see sometimes, but the vibration picks up. So if I do a traditional PSI measurement here, you can clearly see the ripple in our data. Now, as I couple that cavity again, I can measure, and we may or may not get a better measurement. That one looks slightly better. But typically what we see here is you can go ahead and continue to add mass to this coupling, and this may or may not improve your measurements so much. So that one looks a little bit better, but you can see it's a pretty unreliable method. And in general, I'd say just pretty clumsy. This method also can be pretty difficult depending on the test size. So if you have a very large cavity or a very long cavity, that beam and that need to bridge the gap becomes really difficult. And on the other hand, if you have a small test part, whatever you end up bridging the gap between the interferometer and part with is just going to be too lightweight to efficiently couple that cavity and reduce the vibration. And in either case, you absolutely run the risk of actually damaging your parts using this technique. Oh, sorry about that. Now, the next solution we see a lot here is actually kind of just the go get a bigger table method. So here we can add damping mass. This is going to really add cost to your setup, but also it's going to take up some really valuable floor space. And then the next technique here is actually probably one of the more common ones I see, and this is just to measure repeatedly until you get lucky and get what looks like a good measurement. So some days, you might come in and be able to measure, and on your first shot, have a good reliable measurement. But other days, sometimes can take hours before you get a measurement that you're happy with, and even in that case, you're left with a lot of uncertainty. And finally, the last possible solution here when dealing with vibration would be to move to a totally dynamic solution. So these dynamic solutions really always do come with some sort of trade-off, though. You might have added setup time. You might lose lateral resolution of your system. But overall, what I think you really lose here is the simplicity and familiarity that you might have already with traditional PSI measurement. Okay, so because of those limitations and trade-offs with some of those typical solutions, Zygo went ahead and developed a method here that we call Q PSI. And what Q PSI really is a set of software algorithms that will improve upon a traditional PSI measurement. And now it's important to note that these algorithms also do rely on some enabling hardware improvements. So Q PSI is not necessarily compatible with every interferometer. But some of the key benefits of Q PSI Obviously, it will eliminate that ripple or fringe print through in your data. And to the right here, you can actually see two measurements, the one above taken with the PSI measurement mode, and the one right below that, a Q PSI measurement. And this is two measurements of the same exact test part, one taken right after the other. The only difference here is that I switched the mode from PSI to Q PSI. Then another good benefit of Q PSI is that it's also going to maintain the full resolution of your interferometer. So this is different than many of the dynamic solutions where you end up with a reduction in that lateral resolution. And finally, Q PSI tends to be a one-to-one replacement for PSI. This is nice because you don't need to alter your existing setup or cavity geometry. There also aren't going to be any extra calibrations required, and there's really no need to retrain or relearn a new measurement process. So having the ability to see such a significant improvement without changing your workflow or procedure, I think is really important. Okay, so if Q PSI is so great, then let's take a look at how it works. So just to point out here at the beginning, this is a very high-level explanation of Q PSI, but if anyone is interested, we can always follow up with some white papers that go into all the details. So Q PSI is a model-based iterative approach that improves upon an initial PSI measurement. Now that might sound odd at first that we need an initial PSI measurement, but actually that initial phase map or that initial measurement can be pretty low quality. The images here on the right are actually on top there, the initial phase map done with conventional PSI. And then all we've done there is apply the Q PSI algorithms to that same exact data, and we end up with the data on the bottom. So you can see that initial measurement can actually be pretty low quality, have a strong ripple, and actually have a lot of data dropout that we can then recover with Q PSI. Next, what we mean by this model-based approach to Q PSI is that we will model the physical variations that occur during a measurement. So specifically, Q PSI will account for rigid body motions for the components under test. So that's going to account for piston and tilt if you're looking at a flat part, or also account for that axial or power aberration when we're doing spherical measurements. But what's really great is that Q PSI does not require any information about the test part. So we're modeling for the specific setup, but we don't need any extra information. So there are no restrictions on surface shape, cavity type, or interferometer type. And when we put all this together, it really results in this excellent correction over a large variety of errors. Another nice thing here about Q PSI is that there's actually this iteration being done, and that iteration will continue until a quality metric is achieved. So if this metric is not reached, then there's actually feedback from the algorithm that can be provided. And in practice, the Mx software, Zygo software, will provide this if a certain measurement does fail, so you can have some idea on why your measurement has failed. This is very different than PSI, which typically will just, whatever data it gets, it will attempt to analyze and then report that data. You know, there are cases where PSI does totally fail, but it's much more common to see erroneous PSI data. And personally, this is one of my favorite aspects of Q PSI, because I know once I see data on the screen, I can actually trust and really be confident in that data. Now, finally, there are some hardware requirements that enable PSI. The first here is camera shuttering. So we use camera shuttering rather than a full camera exposure in PSI. We do some percentage of total shutter to actually freeze the interference fringes in time. So if those fringes are washing out at all, we're able to get a crisp image of those bright and dark interference fringes. And then the second piece of hardware we need for Q PSI is actually a high power frequency stabilized laser. And this is the laser Zygo actually designs and manufactures, uses specifically for this application. And what that higher power enables is, again, tied into that camera shuttering. So the higher power enables a shorter exposure and even better vibration reduction. All right. Now, finally, there are some limitations to Q PSI. First, one case would be where there's just too much vibration. There are times where your environment is too extreme and your measurement might completely fail, or somewhere in between there where Q PSI struggles, you might still see some small amounts of print through. Also, air turbulence is not accounted for by Q PSI. Q PSI is only going to mitigate those effects of vibration. Turbulence will still need to be addressed through a more typical method, such as averaging, which is normally used. Okay, so now I'm going to switch back over to our instrument here, and we'll take a look at a Q PSI measurement. So the first thing I want to do here is just take one more PSI measurement, and we can see our data still has that ripple in it. And if I tilt these fringes around, you'll see that ripple is going to correspond to that orientation of the interferogram. So to do Q PSI measurement, all I have to do here is switch our measurement mode to Q PSI. And the first thing you might notice there is the entire interferogram gets a lot dimmer. So that's because shuttering is now enabled. So in this case, we're shuttering at 25% the full exposure that we used with PSI. So I just first need to readjust our light level back up, and then using Q PSI, I can go ahead and measure again. And there you can see that fringe print through from PSI is totally eliminated in this measurement. I can go ahead and measure a few more times. Let's see, a couple measurements here. So just by switching the measurement mode, very simply, we are able to mitigate those effects of vibration. Okay, so that wraps up our section here on Q PSI. I'd like to pause now and see if there are any questions.
Yep, so first question we got is when should I average and how much should I average?
So actually, it's a good idea to average most of the time. You know, there are almost no cases where doing some sort of averaging, whether it's 8 or 12 or 16 measurements, it really doesn't take too many averages. But you will pretty much always see an improvement in your data. And then to determine how much you want to average, you normally really need to figure this based on your specific environment. So typically you might run a repeatability test and vary the number of averages, and then you find a suitable level or number of averages given your environment. But actually, there is another feature within MX, our software, which I wasn't going to talk about today, but that is smart averaging. And what smart averaging can do is help you determine, or actually it determines on its own, the ideal number of averages to achieve a set threshold. So you input a repeatability threshold into the software, and then when you go ahead and measure, you might have 10 measurements, 20 measurements. All those measurements will get averaged together, and it will continue to measure until that threshold is reached. So it'll always dynamically adjust to the correct amount of measurements. So whenever that's finished, you can really then be confident in that measurement and that you've averaged sufficiently.
Awesome. So next question would be, why did all your measurements look different?
Okay, yeah. So that's likely due to the turbulence in this room. As I said, this is not the best controlled environment. So that's probably the air turbulence, temperature gradients through this room. So typically there we'd want to go ahead and do some averaging to stabilize each of those measurements. And in that case, we just looked at, I was only doing one measurement without any averaging.
Awesome. I think that's all the questions we have time for right now. Feel free to continue.
Okay, thanks. Okay, so we left off with some of the limitations of Q PSI, those being really extreme amounts of vibration, and that naturally leads to our next technique here, which is dynamic interferometry. So dynamic interferometry, or instantaneous interferometry, is really used in those situations where you have extreme vibration or even extreme turbulence. So these dynamic interferometers can account for vibration like Q PSI did, but really at a much more extreme level. But like Q PSI, they won't compensate for turbulence, but they are able to measure in the presence of that turbulence. And now there are many types of instantaneous interferometers, but they all have a similar operating principle, which is that they all attempt to impart a phase shift onto the interference signal that can then be measured at the same time. So how each interferometer goes ahead and imparts this phase shift, though, can really be quite varied. And finally, another benefit, other than just measuring in the presence of vibration and turbulence, is that instantaneous interferometers are actually able to capture dynamically changing events. So for instance, this might be a case where you want to measure the effects that temperature changes have on a sample over time. So you can go ahead and apply that temperature gradient to a test bar and then dynamically measure throughout time, capturing different sets of data, and then go back in and see how that temperature affected your test part there. So here, let's take a look at actually Zygo's solution to dynamic interferometry, and this is what we call Dynaphase. So what Dynaphase is actually a single frame carrier fringe method. And each one of these frames that we analyze can be actually as short as 12 microseconds. So it's getting really close to a true instantaneous measurement. And as you expect, Dynaphase is insensitive to vibration and turbulence. But what really sets this method apart from some other dynamic techniques or dynamic interferometers is the calibration routines that we use to eliminate residual errors. And I'll be going over that in a few slides, so I'll just leave that for now. And finally, another thing Dynaphase enables is what we call a live phase. So this is a measurement mode where we can generate phase maps or surface maps in real time, allowing for dynamic alignment of optical systems. And we'll also take a look at that. Okay, so Dynaphase utilizes a carrier fringe method, as I say. So here we can take a closer look at that. And basically what we are doing here is introducing a relatively large amount of tilt. This amount of tilt is much more than you would typically perform PSI or Q PSI measurements with. And on the left, or on this picture here, you can see that the fringes aren't really visible, but if we zoom in here, we actually do have a lot of fringes oriented along that diagonal there. And depending on your interferometer, this can be anywhere from 300 to 500 fringes across the entire aperture. And if we zoom in one more time, what we're actually going for here is a 4 pixel per fringe alignment. So what we're effectively doing here is creating a phase shift over every 4 pixels that we can then analyze for a phase map, a transmitted wavefront measurement or a surface measurement. And as I said before, Dynaphase can measure in the presence of extreme turbulence. So because we're able to capture every individual frame so fast, that turbulence effectively gets frozen in time and we're able to calculate a surface map. And now since we can measure so quickly and we can measure that turbulence, which is normally quite random, we can then average many measurements together to negate those effects of turbulence. So on the left here, you can see we have a single measurement. And if I click through a few single measurements, they're all quite random. So all of that is the effect of turbulence. So what we can do, or what I did here on the right, is actually take 100 measurements and average them all together. And what's nice about Dynaphase is because we're capturing so quickly, I was actually able to do those 100 measurements in only 5 seconds. Where if we were to use PSI or Q PSI, that's going to take a significantly longer amount of time. And as I said before, in the case of Dynaphase, we're actually adding a couple hundred fringes of tilt to introduce that carrier fringe. And by doing that, we no longer have a compact geometry for our test setup. So practically speaking, what that means is that if you were to measure without compensating for all that tilt introduced, you actually end up with a surface map like you see here on the left. So that map is a Q PSI measurement taken with the same amount of tilt applied to a typical Dynaphase measurement. And on the right there, you see a Dynaphase measurement after we apply that calibration. So you can see the map there on the left is actually dominated mostly by coma, which is not actually in the test part. So on the right, we can either apply a 2 or 4 point calibration, and those calibrations will account for coma if it was a 2 point calibration, or it'll be expanded to include astigmatism if we go through a 4 point calibration. And we can see the differences between those in our live demonstration coming up. So by accounting for those residual errors caused by introducing that carrier fringe, we can actually be confident that our results will match a conventional PSI or Q PSI measurement. So here on the left, we have a PSI measurement. In the center, we have a Dynaphase measurement. And on the right, we have the difference between them. So you can see how well those different measurements actually correlate once that calibration is applied. Okay, at this point, I'm going to switch over to take a look at a live Dynaphase measurement. Okay, so to do a Dynaphase measurement, the first thing we need to do here is just switch our measurement mode to Dynaphase. And then I'll just pick this option single, because at this point we just want to do a single measurement. So I just go ahead and click measure. And once I click measure, we're brought to this, this Dynaphase wizard, which will walk us through the calibration process. So the first thing I'm going to adjust here is this calibration threshold. So this is set to 1 nanometer right now, which is actually extremely tight. For time's sake, I'm just going to loosen that threshold up to 1,000 nanometers. And what that should allow is us to stop after a 2 point calibration. But if you have a more demanding application, you can go ahead and set that threshold lower as required. So here I can just draw a mask over a region of interest, and then I'll go ahead and click next. And here the first step of our Dynaphase measurement is to align our return spot to this green reticle. So this is going to roughly align our part with the right amount of tilt. And then the next screen here, we see these synthetic fringes, which allows us to finely align the part. Now, if I move this window over though, you can see behind it is the real live display. So we have all of this tilt along this oriented in this diagonal here. But this synthetic fringe allows you to align the part with a more typical interferogram that you might be used to. So go ahead and click next here. And then we're just brought to this screen where we will align the test part in the equal and opposite quadrant. And these two measurements can then be combined to account for those residual errors that we're putting in with the carrier fringe. So once aligned, I can hit next. Now at this point, the software is checking if we've achieved correction better than that threshold. And in this case, it has, so we're presented with a final data set. If we did not reach that threshold, then we walk through the second and fourth quadrant, finish a 4 point calibration. So at this point, I can just click finish. And you see back in the main portion of MX, we have a surface map, which we can then analyze as we typically would with any other measurement inside of our software. Now, if I wanted to go ahead and measure this part again, I can switch my measurement option to production. So since I've done my calibration, I don't have to redo that, given that this test setup is exactly the same. So when I click measure, I'm just brought back to this last fine align screen, and I can tweak my alignment if needed. Then I can just click next. I'll get another measurement. And again, I can just hit finish. And we get our next data set back in MX. Alternatively, I can use this button, and I can just avoid the final alignment if I know my alignment has been stable. And we can see a variety of measurements here, which again are looking fairly random. So I assume I have some turbulence. What we can do here then to mitigate that is switch my averaging up to 100. And if I go ahead, I can click measure. I'll just check my final alignment once more. Tweak that. And this time when I hit next, it'll measure, take 100 measurements and average all of those together. And there we go. We have our next measurement. And this one is 100 averages, so you can see how quickly how quick that goes using the Dynaphase mode. Okay, so that wraps up the demo of Dynaphase. At this point, I'd like to check in again and see if there's any questions.
Yep, so first question I got here is, could you talk about other dynamic interferometry techniques and when is carrier fringe the best?
Yeah, so there are a few other methods for dynamic interferometry. The only other one I'm really most familiar with uses different polarization states to induce that phase shift that then is analyzed for a surface map or transfer waveform map. But what you're going to struggle with when you use any type of polarization technique is testing a part that might have some polarization effect. So if your part has some birefringence, you might not be able to have a consistent measurement over the entire part because your test part is affecting the polarization of your beam there.
Awesome. And next question, what level do you need to switch from Q PSI to Dynaphase?
Yeah, so that's actually a trickier question than it sounds to answer. So vibration actually has both amplitude and frequency components, both of which all combine to really affect how vibration is changing your measurement. So because of that, there's really no hard cutoff on when you make the switch from Q PSI to Dynaphase. Really what I recommend, and probably is the best way, is to actually get a live demo of one of our instruments on site at your location. And at that point, you can say, you know, Q PSI will work here. If it doesn't, then we can move to the Dynaphase method. But actually, it's important to know that any of our standard and current generation interferometers can be enabled with Q PSI and Dynaphase. So at any point, you can pretty much switch between the modes if you've enabled both measurement modes.
Awesome. I think that's all the time we got for questions for this part, so feel free to continue.
Okay, so we looked at Dynaphase measurement. So at this point, I want to take a look at our dynamic alignment mode or live phase. And I'll switch back over to MX here. And to do this, for this measurement, I'm going to be using that beam reducer here. So I'll just bring that into our test setup. And the first thing I need to do here is actually realign our return flat. I want to keep this on axis to our interferometer. So I'll get that pretty well aligned here. And then I'll switch back to our align mode. And I'll coarsely align our beam reducer into the field of view. That's pretty good. And now since I switched our setup here, the first thing we're going to do is actually switch back to a single measurement. What this will do is force us to redo the calibration. Since we're doing a new setup here, a new cavity geometry, we do want to do a calibration for each setup. First thing again, I'll align that mask to our region of interest. And in this case, I want to keep the optical axes of the beam reducer in line with the reference flat, or the return flat. So I'm going ahead and going to tell the software up here that instead of tilting the test part, I'm going to use the tip tilt adjustment knobs on our accessory receptacle to induce the carrier fringe. So here, as before, I'll just click next through the wizard and do our coarse alignment to that green reticle. Click next and adjust our fine alignment. And click next, and then we'll be asked to align in that first quadrant. And we'll do another fine alignment. So here we get our first measurement of the beam reducer using Dynaphase. So I click finish, and as before, that data is brought into the main window of Mx, and we could always analyze this like we do any other measurement. But in this case, I'm going to switch to live phase here under measurement options, and then click measure again. So what we're brought to here is this window where this data map here we actually see is alive. So if I block the return beam here, we're blocking that measurement. And if I go ahead and click this button here on the lower left, calculate Zernike's, I can then show these this real-time output. On top we have a table of the Zernike coefficients, and below we have a bar chart where here I can just adjust the limits of this bar chart. But I can go ahead in the table, check on the different coefficients, whichever ones I'm interested in for my alignment, and those show up in the chart below. So in this case, you can see I have a focus coefficient. And as I adjust this beam reducer's position, we can see that bar go up or the coefficient go up. And just by keeping an eye on that bar, I can quickly dial in that focus pretty well close to zero there. Likewise, I can always do some XY decenters and see how that changes our measurement. So there you can see I'm driving the X coma down, and every now and then you'll see we get some dropout here, but I can just bring that back in by adjusting our transmission flat to ensure we have the correct amount of tilt for that carrier fringe. And then the other thing we can do in this mode is actually toggle on a live display here of our interference fringes. So if you're more comfortable aligning interference fringes rather than the surface map, we can use that synthetic fringe. And again, everything updates in real time. And then at any point that we're using this live phase measurement, I can always go ahead and click next, then click finish. And again, we end up with our final measurement from that beam reducer. Okay, so that really does it for our live phase demo. First, I'd like to summarize a little bit what we went over today. First, we reviewed how vibration affects those conventional phase shifting interferometry methods and a few techniques how to mitigate them. Next, we had a look at some of Zygo's proprietary solutions to handle vibration, those being Q PSI, in those environments where PSI struggles, but the vibration isn't all that bad. And Dynaphase for those most extreme environments in terms of both vibration and turbulence. And finally, we just saw how you can use that Dynaphase mode to do some dynamic alignment with that live phase technique. At this point, I'd like to open it back up and see if there's any questions on anything we went over today.
First question we got is, can vibration result in lower fringe contrast?
Yeah, so vibration, if it's so extreme, you might see a reduction in fringe contrast, but really, this is the point at which it's so extreme that those fringes are getting washed out, and what you're probably seeing is something closer to a gray screen or gray image without any fringes at all. Typically, if you have low fringe contrast, that's more likely caused by a mismatch in cavity reflectivity. So if you're, very common cases, if you're using one of our standard transmission flats, which has a 4% reflection against a highly reflected aluminum or silver test part with 80, 90, or even higher reflectivity, then you're definitely going to see a big contrast loss there.
Thanks. Second question, can I use one of these modes to track effects of temperature?
Yeah, so you can definitely use both modes really to track temperature, but really Dynaphase is well, ideally suited for that. What you can do kind of is start a measurement and then apply a temperature gradient. And then using Dynaphase, you can either measure repeatedly, saving each data set, and then you can go back in and analyze each data set to see how things were changing over time. The other thing Dynaphase actually enables is a movie mode, which is, this mode is actually specific to the Dynaphase interferometer, which was the interferometer built initially for Dynaphase. Now Dynaphase is available on all of interferometers, but the Dynaphase has this movie mode, which you can basically click record, and then up to the frame rate of the camera, we can record a movie of those events that are changing. And then at any point of that movie, you can go in and actually reanalyze those frames for numerical results, and then see how things are changing based on that temperature.
Cool. Another question, do all these measurement modes work with A-spheres and CGHs?
Yeah, so in general, anything you can measure with your conventional PSI, you can measure with Q PSI or Dynaphase. You know, for A-spheres, you're still going to have the same limitations, you know, like slope acceptance. It's just some A-spheres are not measurable with your typical Fizeau interferometer. But once you achieve a null configuration, so maybe you're using a CGH or a computer-generated hologram, then you can definitely go ahead and use either the Q PSI or Dynaphase measurement mode.
Cool. So another question we got is, could you demonstrate the air turbulence effect at all, just by blowing on or waving some air in front of the cavity?
Yeah, so let's see if I can do that. I can switch back here. So to do this, I'll realign my transmission flat, move this out of the way. So let me see if I can grab something here. So one thing you can normally see is if I just put my hand in here, you can see those fringes wiggling just from the heat of my hand. So just by creating that temperature gradient, you can see the fringes move. And let's see, if I jump back into the live phase mode, I'm actually misaligned for that. But I might be able to realign this just by eye. And putting my hand in again, if we look at the surface map here, you can see how quickly that's all varying just from the temperature. If I take my hand out, that should pretty quickly stabilize to a certain point. And hand back in, you can see the effect. The high is right here near my knuckle.
Well, thanks. I think that's all the questions we'll have for now.
Okay, thanks. First, again, I want to thank everyone for joining us today. But before signing off here, just want to point out some of our upcoming events. We're going to be doing a couple more of these webinars scheduled over the next couple weeks, so keep an eye out for those. And then actually tomorrow we'll be starting up some more informal training sessions that you can always register for. You can find the latest updates on those on our homepage at zygo.com. And then, as always, if you have any more questions or needed any more information, please feel free to contact us at inquire@zygo.com or zygo.com//contact right at our website. And again, if there were any questions that we did not get to today, don't worry, we'll be reaching out to all questions submitted via email right after this webinar. And so thanks again, everyone, and have a great day.